So someone asked me in my previous video to explain why I do certain things in the derivation for the loss function, instead of just saying that I do this and that without explaining why I do those things. So I thought I would just make a follow-up video and try to explain the why in the derivation for the variational autoencoder loss. But before we get started, I just want to emphasize that I am not a pure mathematician. I am an engineer first and foremost. So perhaps sometimes when I explain some mathematical topics, I might oversimplify some things or perhaps not explain some other things in the greatest necessary detail to have it make sense, because I think it's more important to understand the overall argument instead of deep diving into some nitty-gritty mathematical detail. So this video will start at the point where I said that the goal is to maximize this log probability. So this is our starting point, and the reason why we want to maximize this, I explained this in the other video. Since we only have data points from this data distribution, the probability that those data points come from this data distribution are 100%. So our model should maximize the probability that some input x comes from this data distribution. That's our starting point. So from here, the very first thing we can do is to marginalize out z. So we can write that this is equal to this log of the integral for p of x given z times the probability to get z over dz. And this process is called marginalization. I explained the marginalization example in my other video, so just believe me for now that this is our very first step. The goal is in the end to get something that we can write a Python function for. The Python function that we want to write will have this form, so it will be definition, I'll call this L. It gets the model as the first input, that will be what we take the gradient with respect for, and then the input x, and then that will return some float, which is the loss. So from this point, can we put this into a loss function? The answer is no, because we don't have access to this latent space over here. So at least the way that this is right now, we can't write a loss function from here. So we need to keep manipulating this until we can. That's the name of the game. So from here, I can do one more step, which is to use the product rule of probability, which basically states that you can take this and rewrite that as this, right? This is a probability law. It's called I'm not exactly sure if it's called the product rule of probability. I just call it that, but this is one of those true statements in probabilities. Okay, but this was just syntactical sugar. We'll revert this later because I just actually don't want to keep writing out this term over here. So I abbreviated it to this basically. Okay, so can we put this into our loss function? The answer is no. So in the variational autoencoder, we had introduced this approximation that approximates this probability distribution. And the reason why we use this approximation was because it is intractable to compute this distribution directly, so we have to approximate it somehow. But in the current form of our equation, we don't have this approximation anywhere. So one thing we can do, and this is just something we can do, there's really not that much more that we can do in this current step. We want to introduce this somehow to our equation and then see what happens. So one way to introduce something to your equations is to use the multiply by 1 trick. And because this is a normal distribution and it won't be exactly 0, you can do this. So there will be no division by 0. And then that will be multiplied with this, right? You can just cancel these out and then you're left with what you had before. But at least we somehow introduced this approximation. So the question again, can we put this into our loss function and, train our model? The answer is no, nothing really changed so far. So we have to keep manipulating. From here, there's really not that much you can do. You can just rearrange some terms. So when we do that, we get this statement. But this right here is the definition for the expectation. And this might actually not be super obvious. At least in my opinion, this is the one step that is the least obvious of all. So in my previous video, I used the example of skewed die to show that this term right here is the definition of expectation. So in the example, I had a skewed die that when you roll it, you get a 1 with a 10% probability and a 6 with the remaining 90% probability and nothing else. So this 1 and this 6, those are the outcomes from a random process, which I will call the probability to get A, right? A can be either 1 or 6. And let me just define another function. I'll call that f. And this other function gets this A, which can be a 1 or a 6 as input. And it returns A again. This is the simplest kind of function there is. You get this A based on some probability that you get from this probability distribution. And the question you could ask is, what is the expected value for this function? If this was a casino, right, and you have to roll this dice, then you're wondering, well, how much money would each roll give me if I get exactly the amount back that I roll? What is my expected value here? So let's say in order to enter this competition, you have to pay $5. And then I could ask you, is it worth it for you to keep playing this game? So in order to answer that, we have to compute the expected value for this process. So in this example, the expected value is equal to the probability to throw a 1 times the value for 1 plus the probability to throw a 6 times the value of 6. And that comes out to be about 5.5. Exactly 5.5. So the expected value is $5.50, but you only have to pay $5 to enter. So of course you would participate and make money. And from this formula, which you can write out like so, you can perhaps see some parallels to this expression over here. In this example, we have a sum. Here we have an integral. So in this case here, we are dealing with continuous values. Over here we have some probability density, so the probability to get A. We have something similar here. It doesn't actually matter that it's conditioned on X. This is some process that gives you the probability to sample this vector Z. So that is similar to this part over here. And then we have this value function. And this function here, that can be anything. It can even, like it does in our equation over here, contain the probability distribution itself. So this function can be anything, even this term. So all of that basically means that we can rewrite this part as this expectation. So the way we write that is that we say that it is equal to the log of the expectation over Q of Z given X. So it must be the expectation over your probability distribution like it does here in this example for the function. And now the function is this part here. This means that we managed to rewrite this formula as an expectation. And the reason why this is useful and why we want to do this is called importance sampling. Because now we have a form where we can sample using this encoder. Remember that this is our own approximation that we can sample from. We can use this encoder in order to estimate this right here. If we look back to our original form, then you will notice again that we have this probability distribution for the latent space. And because this is an integral, we need to sample from, well, both of this and this latent space. Okay, so this part here, that's the decoder. We can use it, but we cannot sample from this latent space. We don't have access to that, but we need to do it because we have an integral here. We have to keep sampling this until we eventually manage to approximate this whole thing. So in this form, it's intractable, again, because we don't have access to this latent space. And through this transformation, we managed to arrive at this form where now we can sample from this encoder, which in turn does estimate this. So by sampling from our encoder, we can in fact approximate this whole part, which we were not able to do before, but now we can. And that is called importance sampling. Okay, so that is pretty cool, but this is still not the form that we can put in our loss function in Python and be happy about it, because we still don't have any means to actually write this in Python, because we don't have access to that. So this means we still have to keep manipulating this formula. So one of the things we can do here is, and you just have to know this, is called applying the Jensen inequality, which states that some function of an expectation is greater or equal to the expectation of that function, so long as this function is concave. In our case, this function is the log function, and the log function is concave. So we can use the Jensen inequality, which is basically the only step we can do from this position. So instead of this equal sign, now we have this greater or equal sign, and that is equal to the expectation of q for z, and now it's the log of this. Okay, but we're still not done yet. This is, again, not the form that we can put in Python. One of the things we can do is to revert this to its original form. So this means we can rewrite this as, and the question, why did we do this? Well, it's basically the only thing we can do when we have it in this form. Actually, from this position, you could have used the log laws to split these two up. So you could have used this. So you could have used this log law to split this up. And another log law that exists is the following. And whether you split this joint distribution to its original form and then apply both of these log laws, or you use the first law here and then turn it back to original form and then use this other law, in the end you will arrive at the same goal. So if we apply both of these laws, we get the following. And again, here it's the only thing we can do. This is not something we can put in our loss function yet, again, because we still don't have access to this. So we just keep moving things around and see what happens. So we basically just keep applying all the moves that we have at our disposal until we run out of moves. Since we still have these two moves, we apply those and then see what happens. Okay, so we're actually getting pretty close. This whole term right here, by the way, is called the elbow, which is the evidence lower bound. I'm not exactly sure what it means by evidence, but it's definitely a lower bound because we have this greater or equal sign here. So if we somehow manage to maximize this elbow, to make this elbow bigger, then that would also make this log probability bigger. So from this position, there's still one more card that we can play, which is called the linearity of expectation. And it is another law that states the following. So basically, if you have an expectation and within the expectation you have an addition, then you can split your expectation into two terms. Okay, so I said earlier that the goal was to maximize this elbow because that would maximize this log probability. But our neural network libraries, they're not designed to maximize something. They're designed to minimize some loss function. So the way we need to define our loss function is in such a way that if we minimize something, then that should maximize this thing, which should maximize that thing. So the way we do that is simply by stating that the loss function is equal to the negative elbow. And if we minimize the negative elbow, then we maximize the positive elbow, which maximizes this log probability. So this means we can slap a minus in front of this whole thing, or multiply this whole thing by -1, and that would give us the following. Okay, so from this position, and we're getting pretty close to the final loss function, the question is, what else can we do? We're still stuck with this latent space, so we can't just put this into our loss function. So we still need to do something about that. And luckily, because we said in the beginning that this latent space is a normal distribution, we can use the definition for the KL divergence. So this whole part here is the definition for it's the negative KL divergence, which means that you can rewrite this whole term as the following. And the KL divergence measures the distance or the difference between two probability distributions. And if we manage to minimize the difference between these two probability distributions, and because we said so, that the latent space is a Gaussian or a normal distribution, if we minimize the difference, well then our encoder will also become a normal distribution because we minimize the difference between these two. Furthermore, because we notice that this is the negative KL divergence and we wrote it out like this, we can further simplify this because the KL divergence, if you have two normal distributions, it simplifies to a closed form, which is equal to this. And this mu and this sigma, they are the outputs from our encoder. Because our encoder is a normal distribution, it will output mu and sigma, and then we can use those to sample the vector z, which is the latent vector. And the summation goes over all the dimensions for the latent vector z. And you will notice that in writing it this way, we have removed any existence of the latent space. So this is definitely something we can use in our loss function. So if we have a look over at this part, this is also pretty easy to simplify. Because if you were to write this part out, you would get the following, which is just the definition for this normal distribution. And one thing I forgot to mention, because the decoder is also a normal distribution, it outputs a mu and a sigma. In practice, we actually don't really use the sigma, we simply just use the mu as the direct value. So in practice, the sigma is set to some constant value. So if we slap the log in front like this, then we get the log over here. So it will be the log of this part, and then this the exponent will disappear, and you are left with this term. But when we take the gradient of our loss function, everything that is a constant will just disappear, because that's just what happens when you take the gradient. So we can have a look at what actually is constant here. Well, this whole part over here is constant, because pi is a constant. We said sigma is also a constant, d, the dimension, is also a constant. Over here on this side, this is also a constant, so that will also disappear and doesn't really play a role when we optimize our model. So all we're left with is this part. And the reason why we're left with this part, well, x is our input, x hat is the output from our decoder, which is the reconstructed value for this x. So this is not a constant. So this whole thing will remain, and this is the definition for the mean squared error. So by doing all of that, we managed to simplify this log term into the mean squared error. From here, we can remove the double negation, and by doing that, we have arrived at our final loss function. So let me just quickly walk over the derivation one last time, but this time as a speed run. We started off saying that our goal was to maximize this probability right here. From there, we just started doing stuff until we run out of options to do stuff. That's basically it. So the first thing we did was marginalization. From here, we wrote it in this smaller form because it's a bit more convenient, but it is still not something that we can put in our Python loss function. And that's our goal. We want to write this in some kind of form that we can write it in a Python loss function. From here, we don't actually have anything to do, so we introduced our encoder and we moved some stuff around. By moving this stuff around, we noticed that this is the definition for the expectation, so we wrote this as an expectation. Then we noticed that we can apply the Jensen inequality because the function, the log function, is concave. So why do we do these things? Well, partly the answer is because we need to do something. So we need to play all of our cards until we run out of options. And the other reason is by rewriting this as an expectation, we now have the expectation over our encoder, and we can sample from our encoder, and we can use those samples in order to approximate this term, which before was impossible to approximate because we needed to sample from this latent space. Because this is an integral and we can't iterate over infinite values, we need to sample from, well, both the encoder as well as this latent space. But because we don't have access to this latent space, we can't sample from this. It means that we can't approximate this whole term. But now that we have written it as an expectation over our encoder that we have access to, we can now approximate this. So from here we applied the Jensen inequality and got this form. So from here we can apply the rules for logarithms, and whether you apply first this law and then this law, or just split this back up to its original form and then apply these two laws, whatever you do, in the end you will arrive at this. And as mentioned, this thing is called the elbow, the evidence lower bound. It's a lower bound because of this greater or equal sign. And by making this elbow bigger, we make this thing bigger. We're not out of options yet. There's still one more thing we can do, which is to apply the linearity of expectation, which basically just says if you have a sum in an expectation, you can split that up into two expectations, like we did right here. And why did we do this? Well, I'll get to that in just a moment. The goal is to maximize the elbow because that maximizes the log probability. But neural networks libraries, they're not designed to maximize stuff, they're designed to minimize loss functions. So if we say we minimize the negative elbow, then that would maximize the positive elbow, which maximizes this log probability. So we take this expectation sum and slap a minus in front of those. And why did we split it? Because by doing that, we notice that this left term is the definition for the negative KL divergence. Since it is the negative KL divergence, minus and minus becomes plus, so we have plus the KL divergence. And the good thing is, because now this is a KL divergence, and we said that the latent space is normal distributed, it simplifies to this closed form, which only uses the outputs from our encoder. And it does so because we said that this is a normal distribution, so a standard normal distribution. And that's why we split these expectations up, because now we can put this pesky latent space into this KL divergence and get this closed form. Furthermore, by minimizing the difference between these two distributions, we shift our encoder to be more like a normal distribution. And that cleans up the latent space, and we can use our encoder to sample new images. For our decoder, that part also simplifies to the mean squared error. It's actually the negative, and it was the negative here as well, but the negatives, they cancel out. So all you're left with is the mean squared error. There's also some other stuff, which I could call a constant plus C, but when you take the gradient, constants don't play a role, they just disappear. And that was it. Now we have this loss function, we can put this in Python and train our model. So I really hope this helped and answered some questions as to why we do some stuff. Again, I'm not a pure mathematician. As I mentioned before, I'm an engineer, so this is engineer math, so take that with a grain of salt. But yeah, I really hope you enjoyed this video. Thanks for watching, and I will see you in the next one.